All right, gentle people, let's go ahead and tackle this problem out. So let's first go ahead and write our equilibrium equation. So in this problem, what we have is N2O4 gas that is going to decompose into NO2 gas. Now be careful, this was given to you guys in words, and so you should balance this reaction out so that you have a balanced equilibrium reaction. So let's go ahead and write our ICE table out. So ICE, and the reason we're invoking an ICE table is we have an initial concentration and we want to find equilibrium pressures such that we can go ahead and calculate Kp. So let's go ahead and talk about our initial conditions. So for N2O4, they say they add a certain amount of gas into our container. Now they don't tell you how much gas, so I'm going to use the variable y to represent that initial pressure. We don't have any NO2 in our container, but what we do know is that this N2O4 is going to decompose. That means its change is going to be negative, and I'm going to make my product, so its change is going to be positive. The ratio is in a 1:2 ratio, and these are based off my stoichiometric coefficients. Lastly, we can go ahead and do I plus C, which equals E, so Y minus X, and then 2X for NO2. Now we have a problem here, and our problem is that we have two variables in our equilibrium pressure. So we have to go ahead and get rid of that. Now we're given a little bit more data here. What we were told is that N2O4 decomposes by 16%. What that means is that the change in N2O4, or negative X, well, I'm going to lose 16%, so 0.16 of my original amount, so Y. Now, I want you guys to know that this says it by moles, and Y represents a pressure. But because of the ideal gas law, a 16% loss by moles is equivalent to a 16% loss in pressure. So what this tells us is that X here is 0.16 Y. So I'm going to go ahead and rewrite my ICE table. So ICE, and now I'm going to use this relationship. So I'm still going to keep this as Y and 0, but instead of minus X, I'm going to put minus 0.16 Y. 2X becomes 0.32 Y, and then Y minus X, or Y minus 0.16 Y, well, this becomes 0.84 Y, and of course that this is still going to be the same of 0.32 Y. Now, at equilibrium, the total pressure is equivalent to 1.5 atm. But the total pressure is going to be the pressure of all my gases. So that means it's the equilibrium pressure of N2O4 plus the equilibrium pressure of NO2. And we just found an expression for each one of these pressures. The pressure of N2O4 is 0.84 Y, and the pressure of NO2 is 0.32 Y. And this all equals 1.5 atm. And so now what I can do is I can solve for Y. In this case, Y equals 1.293 atms. Now what I can do is I can go ahead and calculate my equilibrium pressures by plugging Y into this last line. So for N2O4, it's going to be 0.84 times my Y, or 0.84 times my 1.293. This turns out to be 1.086. And then for NO2, it's 0.32 Y, or 0.32 times 1.293, which turns out to be 0.4138. And now I can go ahead and calculate my Kp. It's going to be my products, 0.4138 squared over my reactants, 1.086. This gets me a Kp value of 0.1577. So let's go ahead and do part B. Under B, we are under some constraints. So we're going to write down our equilibrium reaction. And this time, we're just going to focus on what happens at equilibrium. And I'm going to use a couple of different variables here. In this case, at equilibrium, I know the pressure of N2O4 is some pressure. I don't know what pressure it is under the conditions B sets. And the same thing is true for NO2. At equilibrium, there is going to be a pressure of each one of these gases. Now, your book gives us a little bit of data. It says that if we look at the total pressure, so Z plus W, this has to equal 1 atm. Now, we know that Kp equals W squared over Z, or products over reactants raised to their stoichiometric coefficients. And in part A, we found out what Kp was. It was 0.1577. Now, just because we changed the conditions doesn't mean we changed the Kp. That's why we can use the same Kp. This is being done at the same temperature. Kp is an equilibrium. Emphasis on the next word, constant, an equilibrium constant. So now what I can do is I have two equations, two variables. Let's go ahead and see if we can solve for each one of these. So the first thing I'm going to do is I'm going to rearrange this one on the left-hand side and say that Z equals 1 minus W. And now what I can do is I can substitute this into my Kp expression. So I got Kp. I'm going to keep my W squared up on top. And the Z on the bottom, I'm going to rewrite this as 1 minus W, substituting the left-hand equation into the right-hand equation. Now what I can do is I can go ahead and times both sides by 1 minus W. So I get W squared equals 0.1577, 1 minus W. I'm going to go ahead and distribute, and I'm also going to rearrange things such that I get everything on one side. So if you do that little bit of math, you get W squared plus 0.1577 W minus 0.1577. All of this equal to 0. Go ahead and plug this into a solver. You'll get two values, but the only reasonable one is 0.3260. Remember, you can't have a negative pressure. Now, with this W at hand, I can go ahead and solve for Z. So Z equals 1 minus the W I just calculated out. So 0.3260. So Z here equals 0.674. Now both of these are in ATMs, and so both of these represents the pressure at equilibrium if you want a total pressure of 1 atm. So this leads us to part C. In part C, we want to know what the initial conditions of N2O4 is going to be to get to these partial pressures. So I'm going to start out with my equation. I know this is going to be an ice table because I have an initial pressure and I want equilibrium pressures. So in this case, again, I start out with N2O4 in my container. I don't know how much. I don't have any NO2 gas in my container. This is going to decompose, and I'm going to go ahead and make products. So I plus C equals E, and so I get an expression at equilibrium. Now remember what this is saying. I want this to equal 0.3260 atms, and I want this to equal 0.674 atms, the pressures I found in part B. So now what we can do is we can go ahead and solve for these variables. This right here is probably the easiest to solve because I can just divide by 2 to get what x is. So 2x equals 0.326. I divide both sides by 2, and I get that x is 0.163. Then what I can do is I can work with this expression now that I've solved for x. So y minus x equals 0.674 ATMs. Y, and I know that x equals 0.163, and I can go ahead and solve for y being 0.837. So this question is asking the amount that is dissociated, or in other words, what amount has changed based on the initial amount. So really what this question is asking, what is x, the amount that has changed, over my initial amount times 100%. So I can go ahead and plug in my values. X is 0.163, y is 0.837 times 100%, and we calculate 19.47% of my original sample has decomposed. And this will lead to that 1 ATM of total pressure. I hope that made sense, and enjoy the rest of your day.